How we doing? Things going all right? Hello.
Hello.
What questions do you have? Yeah.
Is there any way to do divided difference faster?
Any way to do it faster? Not particularly, not by hand, or is not. No.
I didn't quite understand how to check for like 5B, how to check the interpolated the results properly.
Oh,
Yeah, I
let's.
was a little bit confused what the method to do that was there.
Choo-choo. There it goes. So notice that if you're interpolating those 7 points, at what degree polynomial would you need to use? 6, right? So if you do a 6th degree polynomial, then that's not, you got a lot of computations, like I mentioned, you got all sorts of divided differences you have to do, right? So the whole point of that was, okay, can you do a lesser degree polynomial and just see? So basically, it would just be a matter of choosing different points in your table and seeing what the points in the middle. So, for example, what I mean by that is maybe you use those 3 and then see if they're close on the other 4. Yeah. Or use that one, that one, that one, that one, and see if they're close on the other 3. Just it didn't matter to see how accurate they were. It's just a matter of playing with it. There wasn't anything that was an exact answer as far as that goes. Just a matter of trying different ones and see what happens. Yeah, because a lot of the point of doing this stuff is to see, are we going to get similar answers and save some computational expense, since there's always going to be errors anyway. That's the idea. Other questions? So, oh yeah, I did. And Masana also told me last night that I had I'd forgotten to change the number of points possible on the homework before I recorded the scores. So if you freaked out briefly about the score, I apologize for that. And thank Masana for pointing out my error. So if that happens again for the next homework, well, when you put the assignment drop box in Moodle, it defaults to 100 points. And that was not what I took it out of when I was grading it. And so when I went in and put it, and the Moodle's weird. When you put an assignment Dropbox in there, it automatically populates a spot for the grade in the grade book. So I didn't think about going back and check, because I didn't know how many points I was going to make it out of when I started. And yeah, I just forgot to change it. So that's on me. I apologize. If you see that happen again, it's very rare that a homework assignment will actually be out of 100. So if you see something that looks really, really off when I record something, just email me and say, hey, by the way, is this right? Because I probably means I forgot to change the points possible in the grade book. Because I do them at separate times. And don't actually grade on Moodle. Obviously, some of you had some printouts that I made to be able to grade on there. So I apologize for that. And thank Masana, because he's the one who told me about it. Like, did I really do that badly? No, you didn't. All right. Any questions? Other questions at all? Yeah, didn't mean to try to, give you a small heart attack. All right. Okay, so we talked about interpolation. We're going to come back to other ideas with interpolation later. Let's I hadn't thought about doing this ahead of time, but let's do it now anyway. Let's talk about one of the problems that happens with interpolation and talk about how we might try to solve it later. Okay, so see if I can do this quickly because I hadn't thought about doing it before class. All right, so let's look at the function. F of x equals 1 over 25 plus x squared. You're welcome. Ideas on what that function looks like? What does it look like? Part of it looks like that. I mean, that's part. All right, what happens as x gets big? In either direction. It goes to 0. Cool. So you're going to have a horizontal axis go to 0. Since I'm squaring the x, what does it look like on either side of the y-axis? Yeah, it looks like the same, doesn't it? It's an even function, right? So you're going to have something that goes up, it's going to get to the y-intercept, and it's going to go back down. It doesn't look like kind of like a bell-shaped curve. Bell-shaped curve technically is a normal distribution, which is e to the negative x squared. But kind of like that, right? Okay. So your function kind of looks like, no, it doesn't kind of look like, let's just graph it real quick. Would have thought about this earlier, I would have just done it. It's all right, we can do this. Do things on the fly. All right, so 1 over 25 plus x squared. Kind of hard to see. No. I'm going to change the 25 to a 1 so you can see it a little bit better. There it is. Well, maybe. I didn't actually type a 1. There we go. Now we can see it a little bit better. I gotta change the scale a little better. It looks like that, doesn't it? The other one was just really flat since I had the 25 in the denominator. All right. So let's say we wanted to try to approximate this function with a polynomial. And the way we're going to do it is just pick some points and see what happens. Okay? I'm not going to pick points necessarily near the end to start with, but let's say we pick, let's say we just do -4, -2, 0, 2, and 4 to start with. And see what happens. Okay? So if I choose those 5 points, -4, -2, 0, 2, and 4, what degree polynomial would we have? 4th, right? Okay. So just as a quick way to solve it, let's lots of different ways we could solve it, but let's just go in Python real quick. I need to change accounts. Oops, I forgot to actually set it equal to something. Okay, so that creates the van der Waals matrix. We've done that before, right? Right. So let me give it a name. And then I need the outputs of the function, right? If I'm going to get the y values associated with those x values. But I'm just trying to find the interpolating polynomial through those 5 points. Right? So I switched it over to 1 over 1 plus x squared so that we could see it. So we would have what? 1 over 17 for the first y value. 4 squared is 16 plus 1. Right? Then we'd have 1 over 5. 2 squared plus 1. We'd have 1 over 5, 1 over 17. Right? And then we should be able to solve this. I didn't actually import the linalg package, so I'll need to type in np.linalg.solve. And I want to solve v comma b for my van der Waals matrix. There we go. So far, so good? Yeah? All right, so those are my coefficients that I would need for my polynomial. The way we had this set up, oh, I got it in the wrong, I didn't put increasing. So the way this is set up is this is going to be our x to the 4th, this will be our x squared, this will be our constant. Right? Okay. So, what if I could just copy and paste this over to Desmos since I already have it up on Desmos? And then just edit it. Ooh, I can. That's fun. All right. So, looks like it's doing a good job going through the points. Right? I've got it going through the points. Here it's going through the point 0, 1. Here it's going through the point negative 2.2. Here it's going through the point negative 4 and a 17th. It's doing a good job interpolating the points. Does it look like a good fit for the function? Not particularly, right? Okay. What might be a better way to try to get it to be a good fit for the function? Add more points. So instead of doing negative 4, negative 2, 0, 2, 4, let's try negative 4, negative 3, negative, just put in the negative 3, the negative 1, and so on up the line. Just add those in there. Okay? So go back over to Python real quick. Let's do negative 3, negative 1, 1, 3. Put those points in there. I could also do this with a for loop, but I'm not doing that right now. Obviously, I'm not doing that right now. When I put in 3, I should have got a 10 on bottom. When I put in 1, I should get a 2 on bottom. That was all I added, right? Negative 3, negative 1, 1, and 3. I don't know if I hit it on it or not. Okay, so there's what we have there. Let's see what we have. And again, pardon me, I have this written as the highest degree term coming first. We now have 9 points, so this should be an 8th degree polynomial. Right? So let's see what happens when I put this over into Desmos. It'll take me a second to get it edited. Ooh, I did not like the double line here, but that's okay. All right, so the constant was a 1. plus. Looks like I'm going to need to move the decimal spot over one place to the left. Make this an x squared. X to the fourth. Oops. Oh, it's because it's missing all these up here. Apparently, it must have been over several lines. Okay. I think this one was going over 2 decimal places to the left. If I would have thought about this before class, I would have just had it all set in Python to graph. 4 decimal places, it looks like. Oops, I must have typed something in. Oh, I forgot my x to the 6th. There we go. That's better. All right, did I go through all the points exactly? Is that better? In the middle, I would say yes, but on the ends, is it any better? No, as a matter of fact, I think it's worse. Right? Notice we're dropping down way low here, dropping down way low here, right? As a matter of, and again, your initial thought would be what? Add more points, right? If I add more points, I would probably go in the halves here. I'm not going to do it because it took me a while to type it back in there anyway. But you could go in the halves here, right? Try those. What you're going to find is that it'll be fine in the middle, but it's going to start looking even more and more like garbage on the ends. Okay? And if I would have used my original function of 25, it would be even worse. Okay? What's happening is something that's referred to as the Runge phenomenon. This is actually the Runge function. And it's basically that horizontal asymptote is causing issues because we're trying to make the polynomial bend into those points, right? And if you think about the higher degree you go, what happens with the higher derivatives? They're going to get bigger and bigger, right? So you're going to get this wild turning quickly that's going to have a hard time making that match. There are ways to fix this. Okay, we used equally spaced points. Maybe that wasn't the right thing to try to do. Right? Maybe we would want more points on the end to try to smooth out the ends and fewer in the middle. And that would be something to experiment with. Okay. Right. So polynomial interpolation is nice. Sometimes it's not. Depends on what you're trying to fit. Okay. All right. So just kind of wanted to give you an example of that. We'll come back to this idea later. Might be an idea to investigate for your final project, for example. That would be something else that you could do for a final project. Okay. I'm going to talk a little bit more about final project stuff next week, so you can start thinking about that. Remember, again, you've got that presentation you'll need to do during Celebration of Scholarship, right, which is the end of April. Okay. All right. Anyway, we're going to come back to polynomial interpolation ideas later. This is one of the ideas we'll come up to. Another way that you can attack this is something that we're going to talk about later as well, is maybe trying to use a single polynomial isn't the way to go. Maybe you want to piece together polynomials. Those are referred to as splines. And we'll talk about splines later. Okay? You all look very excited about it. That's wonderful. Glad you're enthusiastic. All right. So, all of those things that we just mentioned, polynomial interpolation, splines, they all require solving systems of equations. We've just done it, right? We've used Python there just as an example to say, plug it in and try to solve it, right? We've done divided differences. That gave us kind of a algorithmic method of finding the coefficients. But it was kind of another idea of solving a system of equations. So let's actually focus a little bit on system solving. Okay, so spend a little time on this. So what we're going to talk about today, I'm certain many of you have already seen, at least what we're going to start to talk about today. I'm certain many of you have seen, because you talk about it even in college algebra class or algebra 2 or what have you. We certainly talk about it in linear. Okay. But we're going to talk about not only how do you solve it, what does the algorithm look like. We'll talk about, well, how many operations do you actually have to do to solve it. We'll talk about, well, what problems can pop up by solving it this way, and then how you might address those problems. And then later on, either in class or through maybe investigation through a final project, you can talk about other ways that you might try to do this more efficiently, either from a storage standpoint or from a computational standpoint. All right. What's your big technique in linear for solving a system of equations? Yeah, row reduction, right? Gaussian elimination. Usually what we'll start with is what's referred to as naive Gaussian elimination. All right, so what does that mean? Well, let's just do it by example to start with. Let's see if I can, well, hopefully it'll be a halfway decent example. That's okay if it's okay if it's not, because sometimes the not halfway decent examples are just as instructive. Let's look at, this is actually in your text. This is 9.6 in your text. You've got 10x1 plus 2x2, pardon me, minus x3 equals 27. Negative 3x1 minus 5x2 plus 2x3 equals negative 61.5. x1 plus x2 plus 6x3 equals negative 21.5. All right, so we've got a system of 3 equations, 3 unknowns. For our purposes, we're looking for unique solutions most of the time. You know that for a system of equations, how many possible solutions are there in general? What are the possibilities for a number of solutions for a system of linear equations?
0, 1.
Yeah, 0, 1, or infinitely many, right? That's how many we could possibly get. We're not going to worry too much about the 0 or infinitely many cases. At least we hope there's going to be a unique solution when we're done, because we're talking about doing the computations here. So we're not going to worry too much about the other 2 cases for our purposes, okay? Because again, we're just trying to compute things. All right. First thing we always do is make our augmented system, right? So pull out our coefficients. Some books don't put the little vertical line in there. I always put the vertical line when I'm separating my constants just so I can see them. So I have the coefficient. So I have the coefficient matrix, and I've got my constant vector. Okay. All right. Now, we're calling this method naive Gaussian elimination. Ordinarily, when you're doing this by hand, you try not to be so naive. Okay? All right? What would you do first if you were trying to solve this by hand? I'd swap that third row up, right? So I don't have to divide by anything. But that's not what naive means for our purposes. If we're just going to stick this in an algorithm, naive means get a pivot, get zeros, get a pivot, get zeros. Literally naive. Don't have to think about it, right? Just program it, right? And in fact, even more than that is that you wouldn't necessarily need to get a 1 before you start doing eliminations, right? I don't need the 1. I usually just make it a 1 so that I can see what the multiplier is that I need, right? But I don't need to get the 1. So if you're doing this from a naive standpoint, okay, I would work off of this 10 and get zeros below it, right? The whole point of this is to try to think about an algorithm that you might use to do this, okay, if you were actually programming it. Okay. All right. So identify the pivot is certainly important, and we'll talk about that in a minute when we move from naive, not being so naive. But by the way, even though we move from not being naive, I still wouldn't want to flip these rows. Okay. We'll talk about why. This is actually this is the correct row to work off of from a computational standpoint. Even though if you were doing this by a hand standpoint, you would not want to work off that row. Agreed? Okay. All right. So naive standpoint, that's going to be my pivot. Remember we call those pivots the ones that we're working off of to get zeros below it? Anybody not seen this before? Just need to know how much I need to yammer about it. Oh, good. Well, then I'm going to stop yammering so much about it. That's my pivot. I'm going to move down and get zeros below it, but I'm not going to change it to a 1. Okay? I don't need to get the zeros below it. What would I need to multiply this by to make that a 0? Yeah, you need to multiply by a 1 over 10 and 3, right? I get 3 over 10, right? I get rid of the 10 and multiply by what's there, right? So I would do, pardon me, would need to do 3/10 row 1 plus row 2 replace row 2, right? I would make that a 0. Now I got to try to do my arithmetic. That sounds like fun. What 6? That's 6/10. And I'm gonna add it down. All right, so that's gonna be negative 4.4. Since it's tenths, you can do that pretty easily. That's minus 3/10, so that should be a 1.7. That's a lot of tenths. It's 8.1. Is that right? 27 times 3 is 81. 8.1. So I'm going to get what? Negative 53.4. And absolutely pull out a calculator because me doing this in my head is probably going to get errors as I go along. So far, so good? All right. I'm gonna do the next step in a row in the same row here or in a row, I should say, because I want you to think about the algorithm. Notice as you're going, if it's just literally naive Gaussian elimination, I would go down column 1 with a loop, right? As an inner loop, and then an outer loop, I would change my column and go down, right? Now, depends on what you do in linear or in another class where you've learned row reduction. You might do Gaussian elimination or Gauss-Jordan elimination. What's the difference between the two? Do we remember? Gaussian elimination is just lower triangular. Gauss-Jordan is trying to make it diagonal. Get the zeros above as well. We're just going to do the lower triangular part, and then we'll go back through the back substitution. Okay? Again, thinking about it from an algorithm that you might want to try to program. Okay. Also, let's think about how many operations we do as we go along. Okay. We're going to try to extend that and see what the computational cost is for doing Gaussian elimination. Okay. All right. So again, if we think about this from a looping standpoint, I will loop through the rows as an inner loop, and then we'll loop across the columns, right? Not worrying about error checking right now. We'll talk about that in a minute. Okay. All right. The 0 here, we would do similarly. What would be your multiplier here? Yeah, good. Yeah, it'd be 1/10 row 1. It'd be a negative 1/10 row 1 plus a row 3 and replace row 3. This is my notation for doing row operations, by the way. The reason why I write it this way, there are exactly 3 elementary row operations. Swap 2 rows, multiply by a constant, and add and replace, right? Those are the only 3 you get to work with. So that's why I write it in this order. I multiply 1 row by a constant, add it to a second row, replace the second row. Okay? That's why I write it in that order. I know some people will sometimes write it this way, and that really hurts my eyes. That's not the row operation, right? It should be the other way around. Okay. So, in any event, that makes this a 0. Oh, what was this? 0.8? That'll be positive, so it should be 6.1. Negative 2.7, so that should be negative 24.2. I did my arithmetic right. So far, so good? Okay. Again, this is the naive idea, right? Not worrying about our error checking, not changing any pivots. It's literally the same thing every time, right? I'm taking the first, well, I should say the leftmost entry that I have, using that to figure out my multipliers along with the rows below it, and adding down, right? That's why we call it naive. We're not thinking about doing it the best way. We're just doing it the way we know works until we can't. Okay? Does that make sense? Okay. That's the naive part. All right. So now we should be able to do the next one as well, because this is what we're going to work off of, right? Yeah. That was a little bit uglier. Might need some help with the computations here, because no, I'm not doing tenths anymore. I'm doing 4.4ths. But what's going to be your multiplier going down to the next one? Say again? Oh, you're trying to go this way? Yeah, okay, we don't need to go that way. We just need to go the other way. Sorry. Oops. We just need to go this way. Yeah, good. 0.8 over 4.4. Good. Exactly right. And then times row 2 plus row 3 and replace row 3, right? Yeah, we're only going to do the Gaussian part. We're just going to make it lower triangular. Phew, pardon me. All right, so what do you get for, let's move with the calculator tell me what it is, or the next entry in the third row? Say it again? Just tell me a couple more and then we'll round it, yeah? 6.4. The 1? Okay, that's fine. And then the last one? I'm not too worried. There's probably more decimals there, right? Do you have a number for that last one? 91. So what others got? Well, 4.4 goes into 53, what? It's ish 11. What'd you get, Colin? Oh, well, yeah, I think 33 is not too bad. What'd you get?
I got another 38. How about I
Well, if I do 50, well, so I did 52 divided by 4, I would get 13. 8 tens of 13 is 10. 38 seems a little big. Yeah. Anybody else get that? Okay, cool. There. Trying to estimate in my head was hurting it. Okay. All right. Anyway, computation issues aside, the process makes sense for what we have. And now, as far as the reduction goes, we're done, right? We're good as far as reduction goes. And in particular, we've run out of rows, right? If you think about a looping process, I would do column 1, then column 2, then column 3 until I get to the n minus first column, because by the time I get to the nth column, I'm done, right? And we'll come back to this idea when we start counting number of operations. Okay? Is this okay? All right, so now you can talk about how to find the solutions, right? I know what this solution is because I need to divide. Once I get that solution, I can go back up to this previous one and subtract, right? And then go back up to this one and subtract those. At this point, we are good to go to get our solutions. And now you can do a similar algorithm idea for working backward, right? Thinking about how you would program it, right? In this case, if we think about going forward, column 1, I would need to loop through rows 2 and 3. Column 2, I would just need to go to row 3, right? As you're going working down. So if you think about your loop structure, your outer loop would go from 1 to n minus 1, because I don't need to do the last column, right? And your inner loop structure would go from column number plus 1 to the last row. Right, so your outer loop would go from 1 to n minus 1. Your inner loop would go from I plus 1 to n. If you're using I for your counter for your outer loop. And then your inner structure would look exactly the same as far as how you're adding down. And if you're doing things in Python or NumPy, in particular, everything's vectorized, so you can work with the entire rows at a time and add down. You don't have to try to go across each individual row to try to add. You can literally just take row to row and add and multiply. All the stuff's vectorized. You don't have to worry about trying to go to individual elements. Or if you want to play with lists of lists for your matrices, you can do that too. I wouldn't necessarily suggest doing it that way, but you can do it that way. Okay. Matrices are already built into NumPy, so play with that in that way. That's okay? All right. So, and then when you're going through your back substitution again, you'll loop, but you'll loop backwards, right? So you need to start with the right and loop back to the left. And then again, each time you'll need to solve. That gets substituted back up in here. And you'll have to go across this one and plug in things and solve and then keep going back. Right. Good exercise for practicing with trying to get these things to work out from an algorithm standpoint. Okay, think about how you would program that. Anyway, that's the naive version of this, right? This is stuff you've seen, literally not thinking smart about it, just doing it, right? Does that make sense? Okay. From that standpoint, let's think about how many computations you would do. Okay? Literally think how many computations you would do as you're going through this process. Okay? So, if, let's just say we have a matrix to start with. if I have an entry up here and I want to start working my way down that column, how many operations are you going to have to do in that particular column? There's n minus 1 rows that you have to do through that particular one, right? So as I'm working my way down, I've got to do n minus 1 operations all the way down that column, right? But I also have to do those same operations for every column at that time, right? Because I'm not just working on the one column. I have to do it all the way across the row, right? Right? So just to get these zeros, you've got to do n minus 1 operations n times, right? Well, I guess technically it's n plus 1 times because I got to go over to the other. I got to do the constant too, right? And so there's n minus, well, there's n plus 1 multiplications and n plus 1 additions n minus 1 times. So roughly n squared times. And then I've got to go all the way across my matrix. There's going to be roughly n columns. So n squared times n, there's roughly n cubed operations that you have to do, on the order of n cubed operations that you have to do. Right? Roughly. I mean, they actually go through in your textbook in chapter 9, they actually go through and give you a nice little formula for how many you actually have to do. But we're worried about worst case, right? If you're thinking about solving a large scale system, you're worried about worst case. Worst case, there's about n cubed operations. This is more like 2/3 n cubed, but about 2/3 or about n cubed operations. So there's n minus 1 operations, n plus 1 times means about n squared operations across n columns. So O of n cubed ish. For those of you who've done work in computer science, polynomial time is not the worst idea, but of course it's going to go up by the cube of how many rows you have. It gets slow, right? So you might want other ways to try to do more quickly. And there are certain types of systems that pop up in practice where you have faster methods that you can do. For example, something that pops up in practice are referred to as banded systems, where you've got lots of zeros, but you've got a band going across the diagonal. Those you can actually do on O of the band width is better, which is nice. You don't have as many operations to have to do. We will talk about a particular type of system to solve next time that actually pops up in splines. So we'll talk about how you can do that a little bit more quickly. But anyway, generally speaking, Gaussian elimination is kind of computationally expensive. Especially in practice, you get a lot of what are referred to as sparse systems. Sparse means you got lots of zeros in your matrix. If you've got zeros, there's not any point in doing the computations, right? So there's a whole research avenue that people do to try to do sparse systems faster. And there's people working on those things at the U of I in particular. Okay, so anyway, that's naive Gauss. So one problem you already noticed from your perspective, one problem that you noticed was that those computations kind of sucked if you were trying to do it by hand, at least to start with, because I could have done a row swap real quick. Pardon me. Did a row swap real quick, and you worked off the 1 instead of the 10, which would have made your computations by hand easier. But I also told you that that would not be the right approach. Okay? Let me show you why that's not the right approach from a computational perspective. Let me just go into Excel real quick so I don't have to do the computations. You don't need to type these in. You can just follow along with what's going on. Okay? So let's say we had a system where one of our coefficients was exceptionally smaller than the other one for one of the variables. So what I mean by that is, let's say I had 10 to the negative 20th x1 plus x2 equals 1, and then x1 plus x2 equals 2. Let's say we had that system to start with. Without doing any work at all, can you tell me an approximate solution to that system? I don't even have to think about it. Can you tell me an approximate solution to that system? 1, 1 would work, right? 1 plus 1 gives you 2 in the last one. And when I put 1 into the first one, I essentially get 0 for the when I put 1 in for x1, and then plus 1 gives me 1, right? So we should see that our solution here is approximately x1 equals x2 equals 1, right? That's what we should get. Okay. Well, let's see what happens if we try to do this. Let Excel do the computations for us. Let's say I put in 10 to the negative 20th here in for my first entry, a 1 here, and a 1 here, and then a 1 and a 1 and a 2. Okay? And let's just see what happens if we go through the row reduction. And the reason why I'm doing this in Excel is because I can actually do the computations a little bit quicker. All right? I'm trying to do it by hand. All right, so same, again, using naive Gauss, I would want to do, what would be my multiplier when I want to go from row 1 to row 2 to get rid of the 1 below it? Yeah, it'd be 1 over 10 to the 20th, negative 1 over 10 to the 1, all right? So in particular, if I just keep my first row, which I'll do here, I'll just say equals that. I want to take that entry. I want to subtract this and divide it by that. And then times that. All right, so let's talk about how I type that in real quick for the references. Okay. For a particular row, do I want my multiplier to change? No, my multiplier to change all the way across, don't I? Or to stay the same all the way across, all right? That's why I used absolute cell references. Oh, I did this backwards. I'll fix it in a second. That's why I did absolute cell references here. Right? I don't want that multiplier to change when I copy across the row. I do have it backward because I need to divide by the A1 and multiply by the A2. I got my fraction wrong. I would have noticed that when I hit enter. Let me fix this. This should give me 0 when I'm done, right? So my A1s should cancel, and then my A2 minus A2 should give me 0. Okay. So again, the reason why I've got absolute cell references here is that I don't want this multiplier to change, right? Now, if I had more than a 2 by 2 here, I would have left this as a absolute, but I would have changed this one, so I could have copied it down, and it would have changed as I moved down. That part doesn't matter. I'm just telling you why I did it that way, because I want to copy that. Oh, for heaven's sake, just grab it. There we go. That's what we get. Okay. All right. So if we were to solve this now, because we're done with the reduction, there was one step to do the reduction, right? That was it. So if I want to solve this now, I would do that number and divide it by that number. That would give me the x2, doesn't it? Any problems with that one? No. But let's see what happens with the next one. So how do I do this one? I need to take that number and I got to subtract that times that. See what the issue is going to be here in a minute. What's that computation going to give me? 0, right? No matter what I divide, I'm going to divide by this, I'm going to get 0 when I'm done. Is that the right answer? That's not even close, right? From a relative error perspective, that's 100% error. Right? Supposed to be 1, we got 0. That's 100% error, right? That's way off. Okay? So what's the problem? Well, the problem was that in magnitude, this coefficient was significantly smaller than that coefficient, right? So when I used this for my multiplier, I divided it by it. Now instead of being significantly smaller in magnitude, it's significantly bigger in magnitude, right? Okay. So let's just look at this in general of what happened and then see what we can do to fix it. All right. So going back over here to back to some notes here. Let's say we had the system rather than working with that 10 to the negative 20th, let me just call it epsilon. X1 plus X2 equals 1 and X1 plus X2 equals 2. And let's see what happened. Okay. Maybe epsilon is smaller than machine epsilon, for example, which 1 to the negative 20th would definitely be less than machine epsilon. Machine epsilon's around 10 to the negative 16th. So not a huge surprise that the 10 to the negative 20th gave us some error, gave us some issues. All right, so let's think about the matrix. I'd have epsilon 1, 1, 1, 1, 2. What did we do? We did negative 1 over epsilon, row 1, added to row 2, replace row 2 is what we did naively, right? Pardon me. So we did naively, wasn't it? Okay. So that would give me still epsilon 1, 1. Here I would get 0, 1 minus 1 over epsilon, 2 minus 1 over epsilon. Right? And then what did we do? We solved. We said that x2 was equal to, pardon me, the 2 minus 1 over epsilon over 1 minus 1 over epsilon. But what was the issue? As far as the computer was concerned, what did both of those simplify to? What I just circled, each of the things that I circled, what do they both simplify to? Thinking about orders of magnitude, which one's bigger, the 2 or the 1 over epsilon? The 1 over epsilon is much, 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 much bigger, right? I'm taking a really, really, really big number, negative, and I'm adding 2. The other one, I'm taking a really, really, really big negative number and adding 1. Have I changed the numbers much? No. So as far as computation goes, that's going to get rounded to 1. Right? That's what's going to happen. Because it's going to do each of those computations individually. Right? Top one's going to get rounded to the same thing as the bottom one gets rounded to. It's going to get rounded to 1. It's not affecting it anything. Okay? And then when you do the other one, your x1 would be, now it's going to be 1 minus 1 times 1 on top over epsilon. But again, it's going to do this before it tries to divide by that teeny tiny number. As soon as it does that, it's going to get rounded to 0. And this will be 0. Well, I should say it's approximately 0. And there's where the error pops in. So when we just try to apply this naive Gaussian elimination, we're getting what's referred to as catastrophic cancellation. Okay? We've got these things that are these pieces that are way far away from each other, kind of in the decimal point, if you will. So these subtraction things will cancel each other off. You lose significant digits and you lose accuracy in your problem, is what's going on. Okay. So how do we fix it? Well, the way we fix it is instead of being so naive, we want to pick an appropriate pivot, which is what's referred to as partial pivoting. All right. And it's not that big of a deal. I told you when we did the first example that even though you really wanted to switch it up and make a 1 up in the upper left-hand corner, I said really the 10 was the right thing to use and not the 1. What you're going to do is you're going to use the biggest magnitude in the column for your pivot. Okay? Use the largest magnitude entry in the column for the pivot. That's partial pivoting. So you'll swap. You don't even have to, from a computational standpoint, from a computer standpoint, you don't really have to swap. You can leave it in place, right? Figure out which one's the biggest, work off of that one and get rid of the rest of them out of the way. And then go to your next column, figure out what's the biggest of what's left, not in the row that you used. Use that. You don't have to actually do the swapping. Okay? So let's see how that would work just on Excel real quick. If we would have flipped it to start with. Go back over here. Okay. So this should all be the same because I just copied everything down and did the multipliers off there, right? So I should be able to change my system and just it should give me what the results should be. Well, let's say we did 1, 1, 2 on top and 10 to the negative 20th, equals 10 to the negative 20th. 1 and, 1. But in that case, using the largest magnitude in that first column, which was 1, not 10 to the negative 20th. If I use that for my pivot, did we get the right answer? Yeah. We got rid of the cancellation problems. The rounding issues, if you will. Okay? Let's go back through it by hand and see why that worked and see why it was better than the other one. So, flipping back over here. So, we instead, just a second ago, did x1 plus x2 equals 2 and epsilon x1 plus x2 equals 1. Use the bigger magnitude as our pivot. We just flipped it, right? So our matrix looks like 1, 1, 2, epsilon 1, 1. What's our multiplier now to get rid of the bottom? Epsilon, right? So we would have negative epsilon row 1 plus row 2, replace row 2. So your second row should be 0, 1 minus epsilon, and 1 minus 2 epsilon. Right? So now again, when you do your x2, you'll get 1 minus 2 epsilon over 1 minus epsilon. As far as the magnitudes go, that's going to be significantly smaller than that. So you're going to end up with something that's close to 1. And now when you have something that's close to 1, for your x1 now, it's easy. Because now it's just x1 is 2 minus 1 times 1 over 1. There aren't any rounding issues there. We get 1. And so we get the answer that we'd expected. All right. So again, the moral of the story is here that you're partial pivoting. You're going to use the largest magnitude entry in the column to be your pivot. Okay. So not the most convenient for you to do it by hand. It's the one that's going to be the best for the computation as far as the rounding goes. Okay. Because you don't want to get that catastrophic cancellation. That's the bad part. So let's see if we can do the partial pivoting. Let's do. Notice that the example that we started with, by the way, that was partial pivoting. All right. We didn't do it, but that was partial pivoting because the 10 was the highest magnitude in the first column, and the negative 4.4 was the highest magnitude in the second column. By the way, I guess I should have said this. By magnitude, I mean absolute value. The negative sign doesn't matter in your choice for pivot. Okay? All right. So let's see if we can do one with partial pivoting. This is 9.7 in your text. We've got 2x1 minus 6x2 minus x3 equals negative 38. Negative 3x1 minus x2 plus 7x3 equals negative 34. Negative 8x1 plus x2 minus 2x3 equals negative 20. No, it's a positive 2, sorry. I'll put a colon instead. All right, so put it in an augmented matrix form here. Oops. Look like that. Which entry are you going to use for the first column? Which entry are you going to use for your pivot? It'll be the negative 8, right? It'll be this one. Why the negative 8? Yeah, the greatest magnitude, the largest absolute value, right? Yeah. Okay. So this will be your pivot in this case. That's the one you're going to work off of. Now, again, by hand, we would probably flip it, but if you're writing the algorithm for this, you wouldn't flip it. You would just work off of that row. You go identify it and then work and get the rest of them, right? And not reuse that row at that point. Does that make sense? Okay. I'm going to flip it just so we can keep track of it better by hand. But if you're thinking about programming it, you wouldn't actually flip it. Okay. So I'll write it as negative 8, 1, negative 2, negative 20, negative 3, negative 1, 7, negative 34, 2, negative 6, negative 1, negative 38. Flip it. All right. So next step would be to get zeros everywhere else in that column, right? What would be your first, the multiplier to get rid of the negative 3? It'd be negative 3 over 8. And for the other one, it would be 2 over negative 8. Good. or 2/8, I should say. That part okay? Choosing which one we need. Well, let somebody tell me what the answers are, so I don't have to do it in my head. Yeah. You shouldn't have any issues with decimals because they should all terminate since you're dividing by 8. Somebody should be checking my decimals as I go because I'm doing these in my head. People agreeing with my numbers? Yeah. So should have 3/4 plus 7, right? It's negative. Yeah, it's a -2. Yep. Okay. It's like, well, that one I was pretty confident about. Yeah, which one?
Row 3, column 2.
Okay.
-5.75.
Don't we have a -1/4 minus 6?
Isn't it positive 2/8?
Times a -1, right? Oh, it's pints. I was looking at the wrong column. Thank you. Yep. You're right. I was looking at the wrong one. That means my other ones are probably these are probably wrong because I was looking at the wrong row. Thank you. I was totally looking at the wrong row. Negative. I was looking at row 2. 1/4, -1/2. Let's try those. A little better about that. Thank you. I was looking at the wrong row. I was looking at row 2. I think my numbers were right for row 2. All right. Process okay though? What we're doing? Okay. Now that we're doing partial pivoting, what am I going to use for my pivot next? Yeah, the next pivot is going to be this one right here, right? You can go through the computations and get it, but this one is going to be your pivot, right? And you can go through the computations at that point. But now you can also see why if you're actually doing this with partial pivoting, you're not going to want to have to swap it every single time, right? Think about it from a couple of perspectives. One, you're doing computational time. 2, you're doing storage, right? You're actually thinking about how you have to store it. obviously Python's going to have operations that if you really want to do 2 row swaps, it's going to be like, swap the rows, whatever. I don't know if it's it off the top of my head, but there's going to be a command that says swap rows. But think about what you actually have to do to swap a row. I'm going to have to store it somewhere else temporarily, move the other one in there, and then move it back. That's a storage issue if you're talking about doing systems that have hundreds of thousands of variables, right? And that's not unreasonable in today at all. That's not an unreasonable system at all to have to do. If you do anything that's done with anything with data, you probably have hundreds of thousands of data points easily, right? So you've got to not only worry about computational time, you also have to worry about storage costs, which is another reason why that if you're actually doing this, you wouldn't actually do the row swaps. You would just keep track of what row you're working in and which rows you've actually used. These are the things that you need to think about if you're working with large systems, right? It's not stuff that we need to worry about because we're working with tiny systems. But in general, large systems, you have to worry about those things. Otherwise, you're going to take years to solve your problems. And that's not an exaggeration. Literal years to be able to do it. All right. Process okay? You can actually extrapolate on this process. You can actually do what's referred to as full pivoting or complete pivoting, which means not only do you worry about rows, but you worry about columns and do column pivoting, which is weird because you always have to keep track of your variables then as you pivot. But the idea here is to try to eliminate that catastrophic cancellation that we saw. Now, we did obviously a very simplistic, very easy case, but in practice that happens. Subtraction in general is a bad operation to do if you've got lots of significant digits, because if you've got things that are even close in magnitude, you're going to lose significance because all you have is the right end. Okay. So you have to worry about those things as you go along. All right. That's pretty much it with what I want to talk about with doing Gaussian elimination is the partial pivoting. Again, there are lots of things that you can do as extensions of this that you can investigate for your final project if that's something that you're interested in. Okay. You've got that major assignment that I gave you, so I'm not giving you new homework right now. I want you to have time to work on that. All right. Like I said, next week I'll give you some more details as far as what the assignment goes. But I want to. What we'll go back to next time is the idea of sometimes doing polynomial interpolation isn't the best way to go. So you might want to do more approximation stuff rather than doing polynomial interpolation. And so we'll talk a little bit about least squares next time. All right? Have a good one. We'll see you later. I guess a weekend. Have a good weekend.